Making a video here. So here's our problem. We're rotating the region bounded by those functions there, and we're going to rotate it around the y-axis. I drew the picture over here to the left. Okay, it's the green shaded region there, and we're going to spin that around the y-axis. Now, based on what you guys have done so far, right, to spin this around the y-axis, you guys are going to have to use the washer method. There's going to be a gap in it. Okay, you're going to essentially have, well, for part of it. So you're probably going to think of it as this entire part right here, and you're going to spin that around the y-axis, and then you're going to take away the non-shaded portion spun around the y-axis. Okay? So your setup then, to pretend it was completely shaded first, okay, the volume will equal pi times the radius everywhere is 3. So, and we're going from y values of 0 all the way up to, I believe it was 13, right?
Yep.
So 0 to 13 of pi times my radius of 3 squared, okay? And then the height of each one of those cylinders would be dy, okay? Small change in y. And now we need to take out this part, okay? That is just from 4 to 13, okay? So we need to take out the non-shaded portion from 4 to 13 of pi times my radius squared times my height. All the different radii would be this value in terms of y. So you take this function right here, get it into terms of y, and that would be the square root of y minus 4. So this would be your setup to solving this problem using your washer method. Okay? I'm not going to go through and evaluate it here for the video, because the video now I'm going to show you a different method that you could use to solve this problem that is not going to involve a subtraction. Okay? So, this next method is called the shell method. It involves a couple ideas. Okay? The first one that I need you to understand, back when we were in geometry and you found surface area of a cylinder, you found the area of the top circle, you found the area of the bottom circle, then you find the area of the lateral area, or the side, which actually unfolds to be a rectangle, correct? Okay. The area of that rectangle can be found by doing what? Taking what? Circumference times the height, right? Because your circumference of the circle would be your distance across the top, and then the height of the cylinder also matches the height of the rectangle, correct? Okay? So we're using that idea of the area of the sides of a cylinder. Okay? Now, assuming I was able, would be able to roll this tight and not essentially have, let's say I had enough papers that I could roll this so it made a solid three-dimensional figure. So pretend this is solid all the way through. You can't see through it. Okay? What the shell method is basically doing is it's finding the area of the outermost shell, and then the next outermost shell, and then the next outermost shell, and you keep doing that until you get the volume of this three-dimensional solid. So you're just finding the area of the shell, then the area of the next shell just inside it, then the area of the next shell just inside it, and you're really adding all of those areas together to equal the volume of the three-dimensional solid. To explain kind of why that works, remember when we taught you how to find volume of a cylinder? We said, let's find the area of the bottom, which would be a circle, right? Then what do you do with that area of the bottom? Multiply by how tall it is, right? For volume. You're doing the same thing essentially there because you're finding the area of that bottom circle and you're pretending there's just a whole bunch of those circles piled on top of one another. Okay? And when you take the area of that bottom one times how many circles there are, you're finding the volume of that cylinder. It's the same idea except you're working with the outermost shell to the next shell to the next shell to the next shell. Does it make some sense? What questions do you have? Okay, so what I would do, this problem right here, the one that I gave you, I would use the shell method. And here's how I would do that. Okay? So with that rolled up group of papers there, okay, obviously it's not going to be a perfect cylinder. But I would be thinking about this very first shell that I could find the area of right there at the beginning. Then I would find the next shell. And then the next shell. And so on. And as you keep doing that with all these different shells, rotating just the shell around the y-axis, you would create the three-dimensional figure formed by rotating this area around the y-axis. Okay? So now all we need to do is just find the areas of those shells and add them all together. Alright? Well, remember that the area formula would be 2 pi r h, right? For the rectangle of a cylinder, right? Because 2 pi r is your circumference, h is your height. Now, if you think about this, so 2 pi is going to stay the same. Your radius is going to constantly be changing. So I started with that innermost shell, and then I'm slowly moving out to a little bit wider, a little bit wider, a little bit wider, eventually until I get all the way out here to 3. So my radii will just be every possible x value from 0 to 3. So my radius is simply just x. And then my height of all those cylinders will just change with this function. So my height will simply be x squared plus 4. So the area of each one of those, the area of the shells of each one of those cylinders could be represented by this. We want to add all of those areas together, so we want to do this from 0 to 3 times however many shells that would be. So you can simply evaluate this problem using one integral now by finding the area of all of the shells and adding all of those areas together. And I'm just using 2 pi r h. The radii is just changing as we go with x. And the height of each one of those is changing as we go with this function right here. And this way I didn't even need to turn it into terms of y either as I went. Questions?
Over the x-axis, you have to turn it.
If we were rotating it over the x-axis, it would be in terms of y. Yep. So it's kind of opposite how we did the other one. What other questions do you have?
Why am I getting a different answer then? I keep getting 78.
Well, let me stop the video. I'll do that. Okay, anything else before I... You're using the idea of the surface area, the lateral area of a cylinder, and just a whole bunch of those cylinders next to each other. You're taking the shell, or you're adding a shell over and over and over again until you form the three-dimensional solid. We'll do some more with that. Hopefully that gives you a little bit of an idea.
I'm good.